You'll be good though. Okay, so since this is covering I'm supposed to introduce or something. Hello, welcome to the fourth and fifth and final installment of the Excellent Adventure Classical Mechanics series. It was originally supposed to do Lagrangians, but I don't follow rules. We're going to now blast through Hamiltonians and whatever else I can do before these kids all leave the room. So this is going to be a lot of material. This is way more than I should have ever written for you guys, especially since y'all are now in classical mechanics, right? Is anybody past classical mechanics, if that? What are you in, are you in classical mech 2?
Quantum 2.
Quantum 2, okay, what year are you?
Second.
Slow down. So this is more than what most of you have probably seen and what you are authorized to even follow. So what I'm going to do is, this is mostly just a lecture to give you footholds and general ideas of like things that you can hear, so that way you can use them as points of your own research, so that way you can look into things. Because you're going to hear a lot of terms and stuff throughout physics, and for some reason they don't explain things. Like Green's functions, for instance, show up every now and then in physics, undergraduate physics, and then by the time you hit grad school, they just like assumed that at some point previously you'd learned them, where for some reason nobody ever covered that in any of my classes. So there's a lot of stuff like that in classical mechanics as well. So I'm going to try to just hit on some of these topics so you can look into them on your own, in your own research and things. Also, I'm going to post this ungodly amount of notes so that you can look through it. I think it's like 35 pages or something at this point. 15 of which I wrote through all of today. Just a terrible delta function on my productivity otherwise. So, y'all were here for some of the Lagrangian stuff at least. I know some of you. I'm just going to start from Lagrangians, assume that you had followed and understand all of that. Good. So the Lagrangian that we had started with was, or that we have, is kinetic minus potential energy. So assume that we have some Lagrangian that is not explicitly dependent on time. So the Lagrangian is going to be a function of position, velocities, and time. So let's say that it's not explicitly dependent on time. So that would mean that the partial with respect to time is equal to 0. So what that would mean is that if you took the full derivative, it's going to be, by chain rule, going through the partial derivative expansion. Yep. Yeah. And then you've got the explicit dependence, but that's 0 because I ordained it to be so. And what we can do now is we can use the Euler-Lagrange equation to just move around. I'm just going to be tricky real quick. This is just an introduction to what you'll see. So the Euler-Lagrange equation is this bad boy here. So what I'm going to do is put this inside of there. Where am I going to put it? I want to put it here. There. So now what I've got is that the full derivative of the Lagrangian is going to be equal to, so I'm just going to insert that in that part. So now I've got the full time derivative of the left-hand side, d by dt dl on q dot times this term here, dt. Actually, I'm going to name that to be q dot because of notational purposes. The dot is just signifying the time derivative. Plus, and then this whole term that's over here. So now we've got dl by dq dot dq dot dt. So what you can see here is that we've got, let's see, I want to make sure I do things right before going off track or something. Yeah, excellent, good. So we have the derivative of this term, dl by dq dot times q dot, plus the derivative of q dot times that term. So if you want to be tricky and clever and stuff, you can realize that this is actually just the full-time derivative of the product rule. This is a product rule that's expanded out into two terms. First times the derivative of the second, plus the second times the derivative of the first. So we can name this to actually be d by dt of q dot dl by dq dot. Because this ends up being, just to further point out what we're doing, t yeah, which hopefully, if everything's happy, that should be the same thing. So good. So now we've got this expression. So what I'm going to do is I'm going to move This is a time derivative of Lagrangian. That's time derivative of this quantity. I'm going to move stuff on one side and set it equal to 0, you know, just moving things around. So now I've got d by dt of q dot partial L on q dot minus the Lagrangian is equal to 0. So that means that this quantity that's inside of here, whatever this is, it's, when you take the full time derivative, it's 0. So that means it's going to be something that's constant in time, whatever this quantity thing is. I'm going to name this bad boy h. That's a terrible h. H, that's an equally awful h. H is equal to, I'm going to define this to be q dot partial L on q dot minus Lagrangian. So 2 lectures ago or something like that, I had named this thing just arbitrarily to be something I called it the canonical momentum. It's the partial Lagrangian with respect to the velocity of one coordinate. So this is actually that. So this is how I'm going to define this thing. I'm going to call it the Hamiltonian. Surprise. Okay, so the form of this thing, this entity that I've just created, is actually very cool. It comes from, it's a more general transformation than is the Lagrangian transform. So it's not really much of a coincidence that it comes out to be this way. It's got some cool properties that allows us to do interesting things. In fact, it's cool because, I mean, there would be no reason that I'd be doing this if it were not helpful in the end to be transforming it in this way. Of course, so have y'all ever done stuff with Lagrangian transforms? Do you know of any situations in previous classes?
In thermo.
Yeah, Thermo, yeah. Tell me, what were you doing with those?
I don't remember.
All right, good. Because that's exactly how it was for me when I was doing thermo. I had no idea why we were doing Lagrangian transforms. And so I looked hardcore into it, and I was like, oh my god, it's so good, so delicious how it works out again. So I'm going to try to do this in a correct fashion, how I had in my notes. So let's say you have q dot, I'm just going to name this to be v, because it's the velocity, and then you have your Lagrangian on this axis. So because the Lagrangian is going to have, it's going to be 1/2 mv squared minus your potential. If you took the first derivative of it with respect to velocity, you're going to get mv, and your second derivative is going to be m, which hopefully is a positive quantity. So that means that basically your Lagrangian is going to be convex in some direction. It's going to be always like concave up or concave down. Or, well, I hope it's not concave down. Maybe in some weird situations. So that's very important for what you do with the Lagrangian transform, is that it's always concave in some direction. So what we can say is that at this point, for instance, v naught, there has a corresponding slope at this point. We're going to name this slope p of v naught is equal to partial L on v. It's just the slope of this curve at that point, evaluated at v naught. I'm going to name this to be p naught. Okay, so for every single point on here, I can name something like that. So we've got p of v is equal to partial L on v. Yeah, good stuff. So the y-intercept of this line, if I were to take the slope and turn it into just a tangent line that goes through stuff, it's going to intercept at some point. I'll call it b. So I can name this general y-intercept of this curve as being, let's see, v, yeah, p is equal to Lagrangian of v naught, or v minus pv. All right, I just want to make sure I'm good on this stuff. Yeah! Okay, so this is the y-intercept with respect to the velocity on the x-axis and then the slopes of all of them. So because the Lagrangian has the special form is that its second derivative is positive, always. That means it's always going to be curved up like that. That means that for every single slope, if I were to name a slope, there's a corresponding point on this curve that will have produced that slope. There's a unique point. So if I wanted a slope of whatever amount, there's only going to be one point on this curve that would produce a slope of that amount. So you're hitting all of your possible slopes within there. It's invertible in that way. So what I can do is now I can name v as a function of p, because I can name, for every single slope, I can name some location on this x-axis that will correspond to it. So now I can say that b is a function of v of p, p, L of v of p, minus p times v of p. All right, so this looks weird. So, I mean, nothing weird is going on. Nothing useful looks like it's coming out yet. But It's extremely damn useful. It's very interesting because we're changing variables and how we're looking at these things. And we named this Hamiltonian to be a function of just p. And that's going to be minus that y-intercept. So it's going to be p v of p minus L of v of p. Okay, so this is very important because the variables that you use inside of a function mean much more than I ever thought that they did. Through thermo, I did not understand why we were just renaming the arguments of different things. It made me mad because you're taking partials with respect to some things, holding other things constant. Made no damn sense to me. But it's way cooler and deeper than they, for some reason, teach us. So let's say that we've got some function to instantiate this and make it make more sense. Some function of two variables, a and b. And let's say for some reason we can observe and move a, but we can't do that with b. For some reason we're like experimentally incapable or something like that. But we can change the partial derivative of our function with respect to b. So here, hold on. So we can change a, we can't change b, but we can change partial f on b. Well, that doesn't seem like a very useful alternative, but it actually is. So I didn't understand Lagrangian transforms until a few weeks ago, well, their use, because in my own research, I had a function of actually infinite variables, none of which I could change, but I could change the partials of the function with respect to each of the variables. And I was like, man, how could I turn this into some useful functional form that I can actually observe and change experimentally and quantify? You can Legendre transform this. You can make it a function of the derivatives, of the partials of your original function with respect to each of the coordinates. So to instantiate this even more, in thermodynamics, for instance, you have internal energy, and oh God, please yell at me if I mess any of this stuff up because I learned a negative amount of thermodynamics. All I know is the math from it. So in thermodynamics is what seems to be an experimentalist attempt of throwing out all possible math. So the internal energy, which I'll name you, is a function of entropy and volume. Yeah, good stuff, because du is equal to T ds minus P dV for reasons that pissed me off so bad a couple of years ago. So what we've got here is that we've got this internal energy, which is a very useful quantity, this understandably, experimentally verified, quantifiable quantity, internal energy. It's a function of volume. Yeah, I can change the volume as much as I want. That's totally fine. And entropy. So experimentally, it may be a little difficult to change what the entropy is, because the entropy corresponds to sort of the configuration space of your system. And like, sometimes you can change like all of the microstates within your system, but experimentally it's not extremely easy. But what you can change in most situations is if we define this temperature as being the partial of our internal energy with respect to entropy, we can come up with this new Legendre transform of this thing. Because we don't know how to have entropy change, but we do know how to change the partial with respect to it. So how we define this bad boy is we just do, so we name this is actually f of tv, and f of tv is equal to, what is it, ts minus u of sv. Yeah, good stuff. So this is just the Legendre transform of our internal energy. Now, this new Legendre transform entity thing that we don't necessarily know what it is. But luckily, in thermodynamics, we know this thing to be Helmholtz. I think it's with a Z. Good. The Helmholtz free energy. That's badass. I used to not understand why the internal energy, the Helmholtz free energy, and the Gibbs free energy were all these different things. They're Legendre transforms of each other. It's because if you can't change, the entropy for some reason, but you can change the partial of the function with respect to the entropy, you have something more powerful. So that's why we do all these Legendre transforms, or at least that's how I understand it now. I don't know why the hell they did it originally. So that's all we've done here with a Lagrangian, turning it into a Hamiltonian. So let's see, where the hell was I going with this now? Okay, yeah. So now we've got the Hamiltonian. We would like to have some sort of equations that are associated with the Hamiltonian, just like we had the Euler-Lagrange equations with that. So let's get I'm going to write the title now because I realize that I've never written titles when I'm doing this, and I feel like that's useful. Yeah, Hamilton's equations. Let's get these things. So I've mentioned this like every damn lecture so far, but we're not changing any of the physics by doing anything that we're doing. I'm just manipulating and juggling math around, just massaging it into different forms. But by massaging it into these different forms, it can be more tractable and maybe more malleable for future endeavors. Hamilton's equations will produce the exact same equations of motion of the Lagrangian, or the Lagrange equations. But the benefit of this is it produces 2 times the, okay, so if you have n coordinates, n independent coordinates, it produces 2 times that many first order differential equations. Whereas Euler-Lagrange produces n second order differential equations. They're identical, but they're more tractable in some situations, and Hamilton's equations allow us to jump forth with even more things. So we've got our Lagrangian, which is a function of position, velocity, and time. So if I were to take the infinitesimal of this, like well, any good physicist should do, even though I don't even know if this is totally fine. dq, yeah, it's just sort of the partial derivative expansion, but I've just left out the denominator conveniently. dl by dq dot plus partial L on time dt, so this is just the chain rule on each of the arguments. So, all right, remembering where I'm going with all of this shit. Hold on. Yeah, okay, good. So this, I defined to be p earlier, the momentum, the canonical momentum. So I've got dl is equal to partial L on position, d position, plus p dq dot, plus partial L on time, d time. So I can be tricky again, and write this as the infinitesimal of a product minus one of the other terms. So I mean, if I had d of pq dot, this would be p dq dot plus q dot dp. That's just expanding the product rule for infinitesimals. So what I'm going to do here is I'm going to, you'll see in a second. All right, I'm going to insert this thing, just arbitrarily for some reason, and then subtract out the term that I don't want. So that would be q dot dp, and then we have our remaining term all the way on the right for the time. Yeah, okay, and then I'm going to move this over to the left-hand side. Or, well, actually, I'm going to move this to the right-hand side, move everybody the hell else over on the other. Just moving everything around, you'll see. D of p q dot minus L is equal to q, well, I'll do it in order, minus dl dq plus q dot dp minus dl dt. Does that make sense? So I moved this and that guy over to the other side, Lagrangian over to this side. Yeah! Cool, so this is where I want to stay for now. This thing is as earlier defined, the Hamiltonian. It's pq minus L. So I'm just going to leave that guy there right now. Go all the way back over here, and now I'm just going to do the infinitesimal stuff with just the Hamiltonian. So if I have h, which is a function of the position, momentum, and time, then I can do the infinitesimal form of it. dh is equal to partial h on position, d position plus partial h on momentum, d momentum plus partial h on time, d time. All right, so there's good reason for all of this shit. So interesting thing is we got a dh over here, we have a dh over here, so that means these two sides are equal to each other. Just I can bind them in unholy matrimony together. We have partial h on q dq plus, well, fuck this, I'm just going to write it down here. Yeah, here. Write that all the way over here. dl dq plus q. Yeah, sorry, that's a lot of shit, but now we're good.
Are you missing a minus sign?
Probably.
First term.
You're the best. So we've got this. So now we're going to do something tricky that they do in thermal all the time. is they're going to be like, we're going to change one of these variables and leave all the other ones constant. We're not going to change any other ones. This is justified somewhere. Some of the mathematicians did this, I'm sure. So let's say that we change momentum, or let's say we change position, but we leave momentum and time constant. So that means that the d's, the dp, dt, they're all 0 because we haven't changed those at all. So that means the coefficients in front of the dq's must be equal. So we can do this for all 3 of them. And what we end up having is we can have partial h on time is equal to minus partial Lagrangian on time. We have partial, partial Hamiltonian on position is equal to minus partial Lagrangian on position, partial Hamiltonian on momentum is equal to, well, q dot. Does that all make sense? So I've taken the coefficients in front of each of these infinitesimals and just set them equal to each other because I can do that. And from the Euler-Lagrange equation, we have that this. So I'm going to insert that partial L on Q into here. So what we end up having here is minus, yeah, that's all good. Minus partial, or minus full derivative partial L on Q dot. We named that motherfucker over and over again to become momentum, canonical momentum. So this is minus d by dt of the momentum, which I'm just going to name to be minus p dot. So what we have here is Hamilton's equations of motion. I'll write them out a little bit better over here. Excluding the time one, because fuck that one. We have q dot is equal to partial your Hamiltonian on your momentum, and p dot is equal to minus partial your Hamiltonian on position. So, yeah, we have 2 equations to state our equations of motion now. If you just have your Hamiltonian, which we previously defined as being q dot p minus Lagrangian. Yeah, so we haven't done shit. We haven't done fuck all. In fact, we've made it a little bit more difficult sometimes to solve normal problems. I'm not going to solve this here unless by some terrible reason you request this later. But I have a full example worked out on how to solve gravitational potential and things using Hamilton's equations. It's a little bit more enlightening because you get a little bit different stuff, or things are cast in a little bit different form than they were using Lagrangian or just forces. So you can go through that if you want. Most of them just trying to skip through shit real fucking quick so that way you can get general ideas of concepts, and later afterward you can ask me questions of specifics. So this is now the section of my notes that says big boy mechanics, for good reason. Because this is where things get like philosophical. So, something called the Poisson Bracket. Man, I love this guy too. So it's just this thing that I define. So let's say we have 2 functions, f, whoa. Man, I'm just ruining this marker. The marker is inside of it now. Way too much enthusiasm. We have 2 functions, f and g, which are functions of position and momentum. I define the Poisson bracket using this notation between f and g as being partial of our first function with respect to position, partial of our second function with respect to momentum, minus partial of our first function with respect to momentum, partial second function with respect to position. Whoa, Christ. Yeah, so this is like way arbitrarily looking, like constructed, it seems like. And I'm not going to show you all the wonderful things that come out of this formalism, but it's just good to see for now, because you may see it pop up later. Also the things that I'm going to show you come out of it. So let's name G is a Hamiltonian. For instance, let's just plug a Hamiltonian into this and see what happens. So what we'll have is that the Poisson bracket between our function f and the Hamiltonian is going to be, yes, I'm going to absolutely write it all again. Well, that. And from Hamilton's equations of motion, which I just erased for some reason immediately, is q dot is equal to partial h on p, and p dot is equal to minus partial h on q. So we can throw that shit right in here. So we have partial h on p right here. So we know this to be q dot. And we have partial h on q, which is the bottom one over there, so that's minus p dot. So what we have is that the Poisson bracket between any arbitrary function in a Hamiltonian is going to be partial f, partial q, q dot, plus partial f, partial q dot, partial p, yeah, p dot. So what this is this is just the full time derivative of f, because this is just the partial derivative expansion of this in terms of each of its variables. So, I mean, that's just kind of like, of course, I defined it this way such that that would fall out, but it's got so much more like philosophical meanings that come out of it. It's pretty badass. Also, the cool thing is that if your function doesn't just depend on the coordinates, if it depends on time as well, so let's say full time derivative of f, q, p, t is equal to, now we've got this term, h plus the partial with respect to time. We're just doing the full expansion because that's these two terms here, and then the explicit dependence there. In quantum mechanics, so you're the only one who's taken quantum? All right, then deal with this. There's something called Ehrenfest's theorem, which is very interesting because if you take the full time derivative of the expectation of some operator, you end up getting, let's see, this equation. So this is the expectation of some operator, some observable in quantum mechanics, is equal to, now this is the commutator, so if you had matrices, this is equal to A, H, minus H, A. Oh man, all right, that is the commutator. It's if you commute them, basically, subtract the two. The expectation of value of that divided by I H bar plus the expectation value of the explicit time dependence of the operator. This is uncomfortably similar. So when I first saw this in my mechanics class, I was like, what the hell, please tell me your secrets, physics. Everything's connected, and it's kind of beautiful. There's a step in between Poisson bracket and the commutator bracket in quantum mechanics. But they're very similar, I believe. I think Dirac is the one who explored a lot of the similarities here. So very cool. I love that. It always makes me uncomfortable to see these sorts of things. Just a few extra notes that links this a little bit more with quantum mechanics. Yeah, that's where I was going this entire time. It's kind of interesting because quantum falls out of this. But one little quick note, though, is that if you actually took the, I go through all of these things in much more explicit, like rigorous detail. It's terrible in the notes if you want to actually check that out. If you took the Poisson bracket between a position and a momentum, you end up getting the delta function, Kronecker delta. That means that it's 0 if the two, these correspond to different coordinates, and it's 1 if they are the same coordinate. Yeah, right? And in quantum mechanics, you have the canonical commutation relation, which I believe is, so Max Born has it on like his tombstone, because it's one of the few axioms you need to develop like all of a large portion of quantum mechanics. This one, if you take the commutator between x and p operators, you get I h bar times the delta function, which is again damn close. And our old friend I h bar for some reason sticks his dick right up inside of our equation. So that's interesting, uncomfortable, but it's still cool to see this preserved among entirely different branches of physics. I mean, we're doing mechanics here, which is continuous variables. I mean, this is all coming from, I started with action and saying that least action principle. And we've gotten all the way to this point where we're just like a factor away from quantum mechanics and a lot of the things that we see there. So I got a lot of other things in here that I would like to, skip if need be, because this is just unnecessary. Some of the derivations, I highly encourage you to look at some of these things though, because I can just write the answers to some of them to show you the end results. But if you generalize, sorry, there's a lot of shit on this board. If you generalize the Hamilton's equations to just arbitrary numbers of dimensions, you name it's eta, is going to be q1, qn, p1, pn. It's just a vector of all of your positions and then all of your momenta. And then you have this matrix that you define as 0 in by n Yeah, I know. Where these are all n-by-n matrices of zeros. That would be like, 0, 0, 0, 0, 0, until you get to ones, and then you've got the identity matrix here. So that's ones along the diagonal, zeros everywhere. You have minus ones across the diagonal, 0 everywhere, zeros. Gigantic ass matrix. If you define those two quantities, you can restate Hamilton's equations as just, just that. This is the gradient with respect to each of the variables there. So that's pretty cool. If you want, you can look more into the notes for more specifics on how that works and everything. It's just kind of recast in that form. The more interesting thing out of this, the reason I wrote it like this, is this J matrix. There's a little bit more cool stuff that I've found through quantum. I don't know if I've actually been recording this whole time. That'd be interesting. If not, I would be so sad. J. So let's consider if we just had just Q and P, nothing else. Like get rid of all these n's. So then J would be 0, 1, minus 1, 0. Okay, it's just 0, 1, the identity matrix negative, identity matrix 0. Okay, good stuff. What if we had J squared? J squared is 0, 1, minus 1, 0, 0, 1, minus 1, 0. You do matrix multiplication, it's terrible, but minus 1, 0, 0, minus 1, so go minus the identity matrix. We have this new matrix that we've defined, whose square is negative the identity matrix. So, you could look more into this sort of thing, but we know at least there exists a number such that if we square it, it's minus 1. So this is kind of a sort of, I like to see it as like a kind of generalization of the complex number. It's an entity whose square is minus 1, minus the identity, which is kind of cool. Yeah. All right, now next big boy topic. Canonical transformations. Have you heard of those before? I really hope not. Good, yeah. These are intense, yo. So, given Hamilton's equations of motion that I previously stated, and you're just going to have to take my word on it because I'm going way too damn fast to prove any of this or show you how it's used, you can, I think I showed you invariants of Lagrangian maybe, you can change your system of coordinates. You can change the Hamiltonian, everything like that. And if you can change it in such a way that it produces the same equations of motion, we call it a canonical transformation. So, you can move, Q is now Q plus something else. Momentum is like the square root of the previous momentum. The new Hamiltonian is something else. You can change shit however you want, as long as you have, so we're going to name like some Q, some big Q, is now going to be a function of the previous. Some big P is going to be some function of the previous ones as well. Then we're going to name some new Hamiltonian, which Goldstein makes this terrible joke in his book. He says like, oh, we jovially call it the Hamiltonian. I think he's the only one who laughed at that. Nobody laughed, so he just put it in his own damn book. So as long as we have the preserved equations of motion, P, and then P dot, yeah, as long as we have these things that are still satisfied and we still reproduce reality, this is called a canonical transformation. Oh yeah, I'm going to write the title. Canonical transformation. Yeah, there's a lot of shit that I write here and everything. I'm not even going to go through all of that, but you can just trust me. You can change your variables in such a way such that you reproduce the same equations of motion. That should make sense. If not, then read my damn notes. So what's an interesting thing is that if you take this to its limits, you can change your coordinates such that some of them are constants in time. So basically, you've changed to a natural reference frame of the problem itself. Yeah, we can change our coordinates such that in some situations, all of them are constants in the motion. Basically, we've switched ourselves to the reference frame of like the Hamiltonian itself, the Hamiltonian, that K fucker. And when you do this, you reproduce something that is very important in classical mechanics. Next section now. Yeah, so a few lectures ago, or all the previous ones, we've been like slowly creating this like rocket, and we've been like adding some fuel to it, and screwing it and everything like that. And like this lecture, you put the fucking rocket on. We're gonna blast through whatever's left because we're in what, Hell Week right now, or Dead Week, right? Hell Week? Yeah, I didn't realize this semester went by so crazy quick. So now we're at the Hamilton-Jacobi equation. So the Hamilton-Jacobi equation is when you can actually realize this fact. You've changed your coordinates in such a way. Let me see if I can put this in better words and everything. As I previously said. Yeah, in the best possible situation, your variable substitution are now such that Q and P are constants of the motion. So there's sort of a derivation that goes on with this, with generating functions and how you can produce these things. Fuck it. What you end up with is this wonderful equation here. Partial S on T is equal to minus your Hamiltonian. This S, it starts out in my derivation as being something called a type 1 generating function. It's just one of these things. I just rename the variables in such a way that things work out. But this S also ends up being something very similar to the action that we had started with many lectures ago. So what we have is this partial derivative of the action with respect to time is equal to minus the Hamiltonian, this new variable frame. So I find it funny because this is such a bitch to work with, actually. It's really beautiful and works out so nicely, and there's like the culmination of hundreds of years of effort trying to make classical mechanics beautiful. But it actually ends up being very difficult to work with. And Jose and Soliton, I love this. They're like, it's in the introduction to chapter 6. They say, the Hamilton-Jacobi equation is in general not easy to solve. In fact, it is often impossible to solve analytically in closed form, even in physically important situations. But it's important because of its malleability and it's a foothold for what follows on in physics. It's very interesting because it's like the best that we can do. It's going up classical mechanics as hard as we can. Because this is a cool fact that I read in like a biography of quantum mechanics, like a history of quantum mechanics. When they were trying to figure out how to do quantum mechanics well back in the old quantum theory, there was like what was it? Write down how you think it works, like write down a Hamiltonian stuff, like step 3, like be a good physicist, and step 4, like publish on your work. There was no real ritual for doing these things. If I remember correctly, it was Bohr and Sommerfeld, yeah, they found that if you just converted everything into the Hamilton-Jacobi formalism in quantum mechanics and everything, you got quantum mechanics that came out perfectly. So basically, it seemed like quantum mechanics like operated through this for some terrible reason. It didn't want to do the Lagrangians, which are so much nicer. It's more naturally framed in this way. It's more a basic and fundamental concept within physics and reality. So what we're going to do is continue jumping forth. Now we're at action angle variables. And I swear to God, it's almost over, kids. Angle variables. Again, I know that I'm going through these so quickly that you can't even apply this. Like I could not give you a test right now and you have any idea how to use these. But I'm giving you the names of things that I didn't even hear about until I learned about them. And they're very, very interesting things, and I really recommend that you look into and read them. I've got some books here you can borrow if you'd like. Action angle variables is another situation. It's another variable transformation on your coordinates, such that you can produce. Let's see if I got this perfectly right. Such that all of the momenta, we're changing Q and P to what we now have as phi and j, where j, all of the momenta are constants of motion. So what this would mean is that by the Hamilton's equations, well, I'll write it out a little bit better. That's a phi, by the way. So we had this as one of Hamilton's equations. I sort of have it here. This one, that one. And since P is now J, I'm naming J. This is what the equation looks like. If I named this to be a constant of the motion, this is my new variable transformation, this is equal to 0, which means that the partial of your Hamiltonian with respect to your coordinates is 0. So it's a little bit far leap, but that just means that your Hamiltonian will no longer explicitly depend on any of these variables, because the partials are 0. So this means that your Hamiltonian is a function only of this thing we call the action. And this thing over here is called the angle. So with these, it's very useful because, again, you get a bunch of cool shit. I'm not going to go into it, but notes and stuff like that, asking things afterward. What ends up happening is that if you have some periodic motion and you have constant energy, something's going in some direction like this, you can actually rename the system such that phi now corresponds to this thing's like angle on the trajectory, and the action can be defined as PdQ. So this is an interesting. I find this a very helpful and very cool point, because this is what you end up having, is that phi is now your angle that goes all the way around. It's normalized such that it goes from 0 to 2 pi, so you return to the same point on the trajectory. And your action here is defined in terms of your momentum dq. Q is phi here, or whatever. You're good. This is how we call the action. And what's interesting here, again, another leap into why this is a deeper understanding meaning in physics, and why this is so important, and why this is so extremely badass, is that we were able to culminate all of our knowledge into this, is because Bohr and Sommerfeld made the wonderful distinction that if you do all of this terror, this crazy stuff that I've just thrown at you for the last like 45 minutes, if you do this to your physics, and then you set this thing equal to NH bar, you have the old quantum theory. So in my notes, I'm not going to do that here, but you can derive the quantum harmonic oscillator by what you do is I explain how to find the Hamiltonian from the Lagrangian, and then you transform your variables and things. You do it into Hamilton-Jacobi equation. You go to action angle variables. You define your action as this, and then you set it equal to NH bar, and you get the energy states of the quantum harmonic oscillator. It's wrong by the 0-point fluctuation energy, 1/2 h bar omega, because it's the old quantum theory and didn't have everything right. But it's still astounding that you can get so damn close with just pushing classical mechanics as far as you can, and that's it. Like it's really amazing, because this is so fundamental to what reality itself is. Yeah, I'm not going to go into this example either, but basically once you can go even farther to action angle variables, and now you can Fourier expand all of your possible positions and momenta. And once you do that, you can get, well, you just can Fourier expand an observable, basically, is what we call it. And if you have this observable, you've seen Fourier expansions, I'm sure, yeah. If you Fourier expand your position and your momentum, and you constrain upon it, you go into action angle formalism, and then you constrain upon it like, I think it's the NH bar condition, and you have that. You figure out that basically the terms within your Fourier series correspond and have a specific product between them that has to work out for you to get NH bar. You have to have like this new product in existence to get NH bar. I talked about this in my quantum mechanics intuitive whatever lecture, assuming you guys haven't probably watched that. But what's interesting about this is Heisenberg, I believe, is the one who did this. Yes, Heisenberg. He Fourier expanded all operators, all position momenta, into just these series, these endless series, and he called each term in the series by an index of some sort. 1, 2, 3, I, that stuff. And he imposed the condition in H bar, and he required reality to work and everything to not break, because that usually works in physics. And he got this extremely weird product rule of how the indices must work out. And this was 1924, and he sent it to his friend Max Born, who was on vacation. I think, and 8 days later, Max Born came back, and he's like, oh, holy hell, I took a class on this when I was in undergrad, when I was doing my math degree. He's like, this is the exact same product rule for matrices. And he was like, you have just, like basically, for this to work out and have this work exactly as quantum mechanics dictates, you have to have your Fourier coefficients correspond to basically indices in a matrix. So he found that, to extend classical mechanics to fit reality, you have to extend your notion of what position and momentum are. They're not just numbers, they're actually matrices, they're operators, they're these things that have a bunch of different components in them. And I thought that was super badass, because that's interesting, because before 1924, physicists didn't know linear algebra for shit. We didn't know matrices or vectors or anything like that. Now we do it all the damn time. And this is why, because it's actually useful. All right, so kids, that was the entire second half of graduate classical mechanics. I hope it all made sense to you. I think they're having a test next week. If you'd like to sit in on that and see how well you can do. I can give you these notes at least. I'm going to post them on the website as well, so that way you can look through. I skipped like 4 or 5 different sections that for some reason I wrote through today. I should have done science today, it's terrible. If you want to read those, you can. I also suggest these books that you see here. Are there any questions?
What are those books?
These books are Jose and Salaton, Classical Dynamics, a Contemporary Approach. I really like this book because this book presents classical mechanics pretty much how I've been presenting it to you, but much better. And they do it in more modern formulation of how we do classical mechanics, because Goldstein is standard in the field and everything. It's Goldstein's Classical Mechanics, 3rd edition, but he does it like how I feel to be more mechanical, like how we used to do it, like when we were first doing classical mechanics, forces and things like that. I don't like it too much because it's actually applicable. This is more like, now that we've already figured out that everything exists on like a cotangent manifold in symplectic geometry, we're going to go back and recast everything in terms of that. I like that. And this is just, I don't know why I brought this, but this is mathematical methods for physicists. This, if you don't know math, learn it. So get a book like this, or a book that I lent Tim, which I forgot the name of it, but it's all good stuff. It's really good. So yeah, any questions besides what books these are?
When you're changing from I forgot what you called it because you went
I
through all the
blew
sections
through
so fast.
everything.
Anyway, but when you change your coordinates, your p and your q to be constant, would that be equivalent to in quantum when you're changing your matrices so you basically get the eigenvalues?
Whoa. Yeah, so whenever you're doing in quantum mechanics, I thought you hadn't even taken quantum.
I'm taking it right now.
Oh yeah, wait, yeah, that's right. You're in quantum 1.
Yeah.
Like tap water, right?
Yeah.
So there exist transformations, orthogonal transformations, such that like, so you can turn this into, yeah. Let's see, yeah. So times, oh hell, what was this shit called? But yeah, good stuff. Orthogonal transformation. Wow, I'm terrible. I can't. Things that exist like this. If I'm wrong, oh god, please help me. But these are sorts of things that you can do. You can diagonalize things.
Right.
You can turn something into, you've got, what is it? Yeah, all your eigenvalues along the diagonal, and then these are all the eigenvectors and stuff like that, and you've got the inverses on these. These are all eigenvectors going along like that. Yeah, these are transformations that turn something into its more real state. Yeah, and there exists a formalism of classical mechanics that, yeah, that's what we are doing. Sorry. I have notes on that as well. There's a really cool book that I had on doing that sort of thing. It's very interesting. Sorry, I'm trying to remember this stuff. The last time I actually did classical mechanics was a year ago now. So I had to relearn like a lot of this stuff to do this lecture. It was terrible. But yeah, it's very interesting. You do stuff like that. The canonical transformations are very similar to that situation.
Okay.
Yeah. All right, anything else like that? And I made some other shit up for the question. All right, good stuff. Y'all should study for your test now. Hopefully you'll be learning, applying some of this stuff onto your Class Mech 1 test. That'd be real interesting. You're not in Class Mech, right? Yeah, so unfortunately you can't have that joy. But I swear to God, if you pull action angle variables on this test, Curtis is your TA?
Yeah.
Oh man, I'd love to see how you would deal with that situation. I wonder if you'd be happy or if you'd be all pissed off. I'd be extremely